let's look at the postulates of kinetic theory for an ideal gas. What these are basically assumptions that if these are valid assumptions, good estimates, then we can use equations to predict the behavior of a gas. And what we mean by behavior of a gas is the relationship between pressure, volume, temperature, and the amount of gas. So again, these are not exactly true, but if we can say that the assumptions are reasonable, then we can make the predictions using the equations we're going to see. Okay, the first one is that if the molecular size is negligible compared to the space around it. And so what we're saying is the particles are very, very small compared to how far apart they are. And these mathematical equations, in fact, will treat the molecular size as though it doesn't exist, as though it is a point particle. The attractive forces are negligible. In other words, molecules are attracted to other molecules, atoms are attracted to other atoms, but we're going to assume that the gas behaves as though they're not attracted, and that can be true if the particles are really far apart. Those attractions don't take hold, which means the movement will be random. We also assume that no kinetic energy is lost in collisions. Again, movement is random and in straight lines. So kind of a particle in a box, they're not attracted to each other. They're bouncing around independently. And the last one is about the kinetic energy. The average kinetic energy is proportional to the absolute temperature. And when we say absolute temperature, we're talking about an absolute scale like Kelvin, where at 0 Kelvin there's no movement. Okay, so in which cases, which situations would these assumptions be most valid? And so to think about these assumptions we made are basically saying that the particles are really far apart and they're bouncing around independent of each other. They're not moving toward each other and becoming attracted or anything like that. So anyway, when are they going to be further apart? High or low pressures? Be low pressures. And when is their movement going to be less affected by each other? It's going to be at high temperatures. And what size of particles? And on this one, if you look at our first one, we want the size to be negligible. So we want smaller gas particles. So what we're saying is at low pressures, high temperatures, and smaller particles, a gas is easier to predict, and we'll see the ideal gas equation on the next slide. But anyway, so you might wonder like what pressure and temperature we're talking about, and it really varies with the gas because the compound, its size, and also the kind of attractive forces can have a big factor. But just in general, to give you an idea, 1 atmosphere and 300 K, that is about room conditions. And so if we're at about room conditions, we're kind of at the limits for this. But lower pressures and higher temperatures than that, the equations are more valid.